Good morning. In today's session, we will be discussing about some numerical examples on torsion in circular shafts. Okay. So, what is the torque generated by circular shafts or power transmission by circular shafts? Power is transmitted by the rotating shafts. We have already discussed the torsion equation, which is already discussed. Okay. Now we'll be discussing the applications of this torsion equation. Okay. Application of torsion equation. So which is T by J, that means torque by polar moment of inertia, J or IP, okay, is equal to tau by R, okay, and C theta by L. So this is the torsion equation. We will be using that here. So first let us see example. First example, a solid shaft of 200 mm dia has the same cross-sectional area as a hollow shaft of the same material with inside diameter 150 mm. Find the ratio of powers transmitted by the shafts at the same angular velocity. Angles of twist in equal lengths of these shafts when stressed to the same intensity. So here a hollow shaft and solid shaft. Okay. Solid shaft of diameter. Solid shaft, let D be the diameter of solid shaft. D1 we have called it. Okay. Inner diameter of hollow shaft is D and outer diameter is capital DC. So the materials are same. So the Young's modulus will be the same. The rigidity modulus will be the same. Okay. And cross-sectional area, having same cross-sectional area. That means area of solid shaft and area of hollow shaft. Both are equal. It is pi by 4 d1 square or pi by 4 capital D square minus small d square. This is the area of hollow shaft. Okay. Where capital D is outer diameter and small d is inner diameter. So ratios of powers transmitted by the shafts we have to find out at the same angular velocity. Angular velocity is omega, which is given as 2 pi n. Okay, 2 pi n, where n is speed in RPM, revolutions per minute. Okay, so here to find the ratio of powers transmitted, first let us find the area of solid shaft, pi by 4 d1 square, and area of hollow shaft, pi by 4 into capital D square minus small d square. Inner diameter is known, outer diameter we have to find out. What is the condition? Condition is areas are equal. By using this condition, we will find out the outer diameter. So equating these two areas, this and this, okay, we will find out capital D, the area of hollow shaft, the diameter, outer diameter of hollow shaft, we can find out. Okay, yeah. Which is coming out 250 millimeters. 250 millimeters. Inner diameter is 150 millimeters. So thickness will be 50 millimeters. Okay. So outer is 250, inner is 150. So thickness will be 50. Okay. Thickness will be 50. And torque transmitted by solid shaft. Let T1 be the torque, which is given as pi by 16 d1 cube into tau. Tau shear stress into modulus, section modulus. Okay, pi by 4 pi d1 power 4 by T2 is polar moment of inertia, and section modulus is by d1 by 2. So it comes out to be pi by 16 d1 cube. That is section modulus into shear stress tau. Shear stress is same for both the shafts. That is what is given. Similarly, torque transmitted by hollow shaft is, what is it? Pi by 16, d power 4, capital D power 4 minus small d power 4 divided by d. Okay, actually it is 32 here and d by 2, isn't it? So it cancels and you will have d. Understand? So this and this are tau is same here. In both of this, tau is same. So power transmitted is nothing but torque transmitted. Power transmitted is nothing but torque transmitted, because the angular velocity is same. So power transmitted is torque multiplied by angular velocity, isn't it? 2 pi nt by 60. That is what is power. 2 pi nt by 60. So this is nothing but angular velocity. Okay, angular velocity, which is same for both. That is what is given. So power transmitted is nothing but the ratio of powers is nothing but ratio of torques, because omega is same in both. So pi tau cancels. We have the ratio as 1.7. Okay, 1.7. Power transmitted by hollow shaft. This is 850, not 50. 850 here. 850 into 10 cube by 500 into 10 cube. So this is coming out 1.7, the ratio of powers transmitted. So generally the power transmitted by hollow shaft is greater compared to that of a solid shaft of same cross-sectional area. If cross-sectional area is same, length is same, then the power transmitted by hollow shaft will be greater than that of a solid shaft. Okay. For this given data, the power transmitted by hollow shaft is 1.7 times that of the power transmitted by solid shaft. Okay. Yeah. And ratio of angles of twist. Ratio of angles of twist. Okay. So how will you get the angle of twist? The ratio, the relation is tau by r equal to c theta by l. From that you will get theta is tau l by r c. Okay, tau l by r c. And for solid shaft, the angle of twist theta 1 is tau l by r c. So r means the radius. which is 100 mm. D1 is the diameter. So radius is 100 mm. Tau L by length is same and tau is same in both the shafts. So tau L by 100 into C. C is also same as the material is same for both. Okay. And angle of twist for hollow shaft is same. Tau L by RC. We'll use the same. But only thing is here R is 125 because diameter D, outer diameter D is 250 mm by 2. That is 125. Okay. So angles of twist of hollow and solid shafts will be in the ratio of theta 2 by theta 1, which is 100 by 120. Okay, from this we'll get it as 100 by 120. That is 0.8 is the ratio of angles of twist. Okay, the length and shear stress being same and material also is same, isn't it? So the angles of twist will be in the ratio of 0.8. Okay, so that is first example. Now let us see the second example. The steel solid shaft of 60 mm dia is to be replaced by a hollow steel shaft of the same material with internal diameter equal to half of the external diameter. Find the diameters of hollow shaft and saving in material if the maximum allowable shear stress is same for both the shafts. Okay, so we have to replace a solid shaft of 60 mm dia by a hollow shaft of same material. Same material means C is same. Rigidity modulus is same for both. And what is given is the external diameter is 2 times that of internal diameter. Equal. The internal diameter is half of the external diameter. That is what is given. So if D1 is external diameter, small d1, capital D1 is external and small d1 is internal diameters, then D1 is equal to small d1 equal to capital D1 by 2. So we have to find out these diameters. The condition given is shear stress is same for both. Maximum allowable shear stress is same for both. Okay, tau is same. Tau is same. Okay. So here capital D is given as external diameter and small d is internal diameter. So we'll use the same notation here. So the torque transmitted by solid shaft is given as, here the diameter of solid shaft D1 is given 60 mm. So torque transmitted is given by pi by 16 tau dq, okay, isn't it? And that is for hollow shaft. The torque transmitted is pi by 16 tau capital D power 4 minus small d power 4 by d, capital D. Okay, so don't get confused here. The denotation is different. Okay, D, capital D power 4, and small d is 0.5 times capital D. So if it is taken as D1, then it is clear. Here also you can take it as D1 and small d, which is capital D1 by 2. And this is D only, the diameter of solid shaft. Yeah, you are getting T1, the torque transmitted by hollow shaft is this one, and that for solid shaft is this one. Okay. Yeah. So here the condition is, what is the condition that we have to use? Torque is same, isn't it? We have to replace the solid shaft by a hollow shaft, which produces the same, which transmits the same torque, isn't it? And in this, the maximum shear stress is same. It is given. Okay. So from this, you will get the external diameter as 61.3 and internal diameter as 30.65 millimeters. Okay. And saving in material. How will you find the saving in material? Saving in material is weight of hollow shaft divided by weight of solid shaft. Okay. Weight is unit weight multiplied by volume, isn't it? Unit weight multiplied by volume of hollow and solid shaft. Unit weight is same for both because material is the same. So volume, length is same. So area of hollow shaft divided by area of solid shaft. Length being same. So finally you will have this ratio equal to ratio of areas of hollow and solid shafts. Okay. So the ratio of saving in material you need. So weight of solid shaft minus weight of hollow shaft. Weight of solid minus weight of hollow divided by weight of solid into 100. That gives the percentage saving in material. So that is area of solid shaft, area of hollow shaft divided by area of solid shaft. Because the ratio of weights is equal to ratio of areas. Length being same and material being same, isn't it? So you will get this as 21.7% material is saved, okay, by using hollow shaft. It means same torque, to transmit same torque, it requires less weight of hollow shaft, isn't it? It requires material for hollow shaft lesser than that of solid shaft for transmitting the same power. Same power. Okay. That is second example. Now let us see another example. A solid shaft of 80 mm dia is to be replaced by a hollow shaft of external dia 100 mm. Determine the internal diameter of the hollow shaft if the same power is to be transmitted by both the shafts at the same angular velocity and shear stress. So angular velocity and shear stress are same. Shear stress means tau are same. Also the same material. Are they of same material? It is not here. But the same power, they have to transmit same power. Okay. So let small d be the internal diameter and tau is the shear stress developed in both the shafts. Okay. So the power transmitted, torque transmitted by solid shaft is this 5/16 tau dq, and torque transmitted by hollow shaft is 5/16 tau capital D power 4 minus small d power 4 by capital D. Capital D is external diameter which is given, and diameter of solid shaft is given. We need to find out the inner diameter of hollow shaft. Okay, inner diameter of hollow shaft. And what we know is the power transmitted is the same. Power transmitted is same for both. That means T1 solid and hollow. Let us take this way. T1 into omega, the angular velocity equal to T2 into that is 2 pi into the 60 power transmitted. Omega is 2 pi n by 60. This is in radians per second. Angular velocity is in radians per second. And n is in revolutions per minute. N is in revolutions per minute. Okay. So by using this here, omega is same, so T1 is equal to T2. That's what we have used here. So pi by 16 tau cancels on either side. So you will have this relation from which we will get small d as 83.6 mm, 83.6 millimeters. Okay, that's all. We want to find out the inner diameter of hollow shaft to transmit the same power at same speed and same stress. Okay, stress is also same, tau is same. This clear? Now let us discuss one more example. Last example for today's session. Okay, a solid aluminum shaft 1 meter long and 50 mm diameter is to be replaced by a hollow shaft of same length, same outside diameter, that is 50 mm, so that the hollow shaft could carry the same torque and has the same angle of twist. What must be the inner diameter of hollow shaft? So the condition given is it has to carry the same torque and the angle of twist is also same. Okay. Yeah. Length of aluminum shaft is 1 meter and diameter of aluminum shaft is 50 mm. Length of steel shaft is also same. Outside diameter of steel shaft is also same as the solid aluminum shaft. Okay. Yeah. Modulus of rigidity for aluminum is 28 gigapascals and that for steel 85 gigapascals. Okay. Is it steel or some other material? Because for steel this is not 85. Okay. Yeah, it is modulus of rigidity. So 85 into 10 cube. That is okay for steel. Okay. And inner diameter is unknown, which we have to find out. Okay. So the polar modulus of aluminum shaft is pi d power 4 by 32 external diameter. Solid shaft, isn't it? So diameter is 50. Pi d power 4 by 32 gives the polar modulus, and we use this relation. T by j equal to c theta by l. And theta is TL by JC. See, TL by JC. Angle of twist for aluminum and angle of twist for C. Okay. They should have the same angle of twist. So theta A and theta S are equal. Okay. We have to equate them. So equating theta A to theta S and also substituting TS equal to TA and LS equal to LA, isn't it? The lengths are same and torques transmitted are also same, isn't it? What is given? Have to transmit same torque. So TA and TS are equal, LA and LS are equal. So from which you will get diameter finally as 45.25 millimeters. Okay, so we have used here the given conditions. Torque and the lengths are equal. Torques transmitted are equal, lengths are equal. Okay, and also angles of twist theta A and theta S are equal. So using these conditions, we will find out the inner diameter for steel shaft. Okay, yeah. That's all for today's session. Thank you. We'll discuss some more examples.
Like, share and subscribe. Hit the bell icon for more updates.